Welcome to a second video on the chain rule for functions of two variables. In this video we'll determine the partial derivatives of a function of two variables with two independent variables. In the previous video we discussed how to determine dz dt with a function in two variables with one independent variable, as we see here. But now we're going to take a look at determining the partial derivative of z when z is defined in terms of x and y, but x is in terms of two variables and so is y. So to diagram this, we start with function z that's defined in terms of x and y, but then x and y are defined in terms of s and t. We can use this tree diagram to help us remember the formula for the chain rule. Meaning if we want the partial of z with respects to s, we need to follow all of the paths down to the bottom that end in s. So the partial of z with respects to x would be this branch here. Notice how we go from z to x, and now we have to go from x to s, which would be the partial of x with respects to s, as we see here in the formula. And now there's also a path to s to the right. The first path leads from z to y. That represents the partial of z with respects to y, as we see here. And then from y to s, that would be the partial of y with respects to s, as we see here. And then to determine the partial derivative of z with respects to t, we would just follow, meaning we go from here to here. This would be this half of the chain rule. Meaning on the right we would go from z to y and then y to t, which represents the second half of the chain rule. Let's go and take a look at some examples. Here we want to find the partial derivative with respects to s and t. Let's start by finding the partial of z with respects to s. So we're going to first find the partial of z with respects to x, treating y as a constant. So the derivative of sine 2x is going to be cosine 2x times 2. So we'll have 2 cosine 2x, and then times the constant cosine y, times the partial derivative of x with respects to s. Well, here's x, treating t as a constant, we would just have 2, plus the partial of z with respects to y. So sine 2x is now our constant. The derivative of cosine y is going to be negative sine y. So now let's multiply these together and then replace x with 2s plus t and y with s minus 2t. So we have 2 times 2, that's 4. And then for cosine 2x we'll have 2 times 2s plus t, that'll be 4s plus 2t. And then we have cosine y. Well, cosine y will be cosine of s minus 2t. Over here it's going to end up being minus. We have sine 2x sine y. So we'll have sine of 2 times 2s plus t, that's 4s plus 2t, times sine y, and y is s minus 2t. Now we'll go to the next slide and find the partial derivative of z with respects to t. So for the partial of z with respects to t, we're going to have the partial of z with respects to x again. The derivative of sine 2x, that's going to be cosine 2x times 2, or 2 cosine 2x. And cosine y would be our constant. Again, we had this on the last screen. Times the partial of x with respects to t, that's just going to be 1. Plus the partial derivative of z with respects to y, so sine 2x is a constant, and the derivative of cosine y is going to be negative sine y. So we have sine 2x times negative sine y. And then we have the partial of y with respects to t. Well, here's y, so s is a constant. The derivative of negative 2t would be negative 2. Let's go ahead and rewrite this and also replace x with 2s plus t and y with s minus 2t. So here we'll have 2 times cosine 2x. Well, if x is 2s plus t, 2x will be 4s plus 2t. And then cosine y is going to be the cosine of s minus 2t. Now here we have a product of two negatives, so we're going to have plus sine 2x is going to be the sine of 4s plus 2t, and then sine y is going to be sine of s minus 2t. And that's going to do it for this problem. Let's go ahead and take a look at one more example. Here's our function z in terms of x and y. Here's x and here's y. So let's start with the partial of z with respects to s. So we'll start by determining the partial of z with respects to x. So we're treating y as a constant. We'd have e to the xy times, if the derivative of xy would be y, times the partial of x with respects to s. Well, here's x. So the derivative of s squared would be 2s plus, this would be 2t, plus the partial of z with respects to y. Now we're going to have e to the xy times x times the partial of y with respects to s. So that's a constant. This would be 2t. For the sake of time, I'm going to go ahead and leave it like this. Let's clean this up a little bit. I'm not going to perform the substitutions this time. We'll have y e to the xy times 2s plus 2t plus, this will be x e to the xy times 2t. Again, we could perform the substitutions here, but it'd be pretty messy and a lot of algebra. The whole point here is to get practice with the chain rule. So let's go ahead and determine the partial derivative of z with respects to t. It's nice to have it on the same screen because we are going to see some repetitions here in these partial derivatives. Meaning the first partial is the partial derivative of z with respects to x, which we found over here, which we found to be e to the xy times y, times the partial derivative of x with respects to t. Well, here's x, so that's a constant, so we'd have 2s, plus the partial of z with respects to y. Again, we found that over here it was e to the xy times x, and then the partial of y with respects to t. Well, here's y, s is now a constant, so we'd have 2t plus 2s. Again, we're going to leave it in terms of x's, y's, s's, and t's, but let's clean it up a little bit. We could rewrite this as y e to the xy 2s plus x e to the xy times 2t plus 2s. I'm going to go ahead and stop here for this video. I hope you found these examples helpful.